Oh, yeah.
Okay, we're live.
That was silence to me because I kept saying, a couple times I said things I regretted saying.
Okay. Yeah, Matt, can you see my screen? Yeah, okay. So today we'll go over this paper briefly, the GPU kernels for Block-Sparse weights.
You can still see chat
paper
if you
released
want
by
on the YouTube page.
Scott Gray, Alec Radford, and Deidre Kingma from OpenAI. They also have an associated blog post in here. I'm just going to focus on the paper. I think the blog post is redundant. The paper has more information. I'm going to stick with the paper for now. But this blog post is also there if anyone wants to look at it.
So this paper just like is it published or is it just a?
Yes, I was trying to figure this out. I couldn't find it on arXiv, even though Google Scholar cites it as an arXiv thing, but it's not an arXiv as far as I can see. It's just on this website.
I thought it was an arXiv actually.
Yeah, it's formatted like an IPS publication.
It used to be formatted.
Yeah, but I couldn't find it on arXiv.
That's why it wasn't published in the journal.
Yeah, and it's actually there's like grammatical mistakes and small things here, so I don't think it's like fully published.
Well, that's why it felt a little bit like, and
It's
then
a
I
little
was
bit-
like, but then we're all talking about is where it come from, you know?
Yeah, so it's a little. I think it's not a fully done paper. I think in that sense. But the basic idea here is, I think, very related to us is stuff that we're interested in. Just how do you get sparse networks running fast? And their whole take is, I think, is a really good discussion of block sparsity, which is, I think, sort of the limit of what you can do with GPUs in dealing with sparsity. So I put down a bunch of sort of high-level questions that we can go over, and Jeff can add to that.
No, I'm sure. I was just saying sometimes last night, I kind of understood all the words of the paper, but I didn't really understand what that one, how this maps onto networks, and it's confusing.
So, so I'll go over the questions, and I'll sort of go back and forth between the paper and the whiteboard. This is not a planned presentation at all, and anything other than a little bit. So just jump in whenever you guys want. Not that I can stop you. So first of all, what is block sparsity, and why is basically the idea is here, if you think about two layers of neurons, so a layer of inputs here and a layer of output neurons here. The typical scenario is you have completely dense connectivity, so everything here gets input from all other neurons with various weight values, and you can display that as a matrix like this. So you have n input units and m output units from this layer. You have an n by m matrix. And the problem there is that the number of weights scales quadratically with these numbers. Block sparse weights are shown here, and basically you have, if you look at a matrix, here you have blocks of dense computation matrices. Okay, so anything that you can draw like this is a block sparse matrix, and everything else is forced to be zero. And you can specify the block sparsity with a mask over the weights like they have on the right hand side here. Okay, so this here you have a 1 wherever there's a block of dense weights there. The reason for doing this is that for GPUs, doing a dense matrix multiply is extremely efficient, and they're optimized for that. And this converts a large dense matrix into a bunch of smaller dense matrices. Okay, so each one is treated as a dense matrix, and then you can just apply GPUs here.
So, well, that was my first question. My first question, okay, great, you break this up into a bunch of little problems. Are they then really considered separate little problems and you allocate them to GPUs as you want? Is that the idea?
I haven't looked at implementation, but that's my guess.
And I don't know enough about GPUs to understand, like, okay, well, these are small blocks. So how does a GPU handle small blocks? I mean, I have a GPU, I don't have a good enough sense for how GPUs work. but assuming that they like to have these big matrices and running up to a certain size.
So there's gonna be some overhead for setting these up, each one of these, and so when you have a large matrix, it's fine, the overhead is small. But now you're making it into smaller and smaller dense matrices, so the benefit of doing that gets less and less as these get smaller.
Yeah, and so does a single GPU run simultaneously multiple blocks?
Yeah,
Okay, so you can set it up that way. It's like sort of parallel processing.
yeah. You can have, I think, thousands of threads going in that GPU.
Right. So this is a theoretical partitioning of a problem, which then you feed into a GPU in a more dense form.
Yeah.
The GPU actually executes a bunch of these at once, as much as you can tile them in there.
And then it just reconstructs the output.
Yeah. So, okay.
Yeah, and I think this is a key issue for here too, is kind of the size of these blocks matter. Because as you get smaller and smaller, the overhead of running each one becomes a bigger percentage. Hey, Vamsi, welcome. Feel free to jump in. Yeah, I'm just explaining the basics of Block-Sparse here.
Okay.
So as the size of these blocks gets smaller, the overhead associated with each block, I'm assuming it's a constant or something, and then it becomes a bigger fraction of the compute cost. So in here, they say they can go down to 8 by 8. That's the smallest they go under, but all the stuff they record is on 32 by 32 size blocks. So I think that's kind of the sweet spot for them. 8 by 8, probably the benefits are not.
What would be the capacity of a typical GPU? What is its native size you could run without having to divide it up? I mean, is even that a reasonable
The
question?
fully connected matrix?
Yeah.
20,000.
20,000-ish.
At one time. I mean, it's not, you don't have to partition that up. Okay.
Yeah, you can it's pretty slow.
Oh,
But
I thought they were fast.
I mean, you'll run out of memory once you start getting far above that.
Okay.
Depends on how you split across multiple GPUs and stuff.
And this is important to us. Most of the sparse matrices that we deal with are not Block-Sparse. They're kind of all over the place. So this is the same as a Block-Sparse matrix with a 1 by 1 block.
Yeah.
So this issue is actually kind of important to us. If they could go out to 1 by 1, then it's fine.
Well, then it would be no blocks.
No problem.
Yeah, exactly, yeah.
One standing question I have is how, like, the size of your block actually affects, like, the final accuracy of your model.
Yeah, we don't know.
Yeah.
We haven't really studied block sparsity at all. And that's something that maybe, comes out of this. Maybe we should, but right now, we don't have anything enforcing.
So my assumption is that once you pick these blocks, you got to stay with them, right? I mean,
You can reconfigure them.
You can change them.
well, okay.
You can learn them too.
So let me ask the question. So like on our side, the left side there, we have this sort of bit by bit sparsity, if you will, right?
Yes, I'll just call it.
Can I translate that into 8 by 8 blocks or 32 by 32 blocks? I don't even know what that means.
You can, because within each block, you can have zeros in here. It's totally fine.
No,
You can just treat it
but
as
the whole point is we don't want those zeros in there, right?
No, you don't want them, but
Can I take the 32 bits the 32 connections I do have here and put them in a block? Is that even a useful question?
I think it makes sense if you think about is there a coordinate transformation basis for the two vector spaces?
Yes, I guess that's the question.
That you can get some type of block form.
yeah. So they mentioned this thing, which I haven't
That'd be a lot
read
of
up
that
on.
too, right?
Yeah, that'd be a lot of overhead as well.
Yeah, so some of the stuff they do is they have a block size and then you go through a fixed shuffle. And then that leads to a random matrix, but you do it all in this, you do the multiplications here. This is a one-time shuffle. And I haven't really internalized whether that would work for us or exactly what that means, but they mentioned that.
So, but I have one question from my side.
Yeah,
Is so the location of the sparse blocks in the bigger matrix, is that a trainable thing, or is that how do you figure out those locations?
yeah. So I think you can certainly change this dynamically. There's probably a little bit of cost to changing it, but not much. So at least every epoch or every mini batch, maybe even you can change these. So I don't.
Okay,
think
so the location is learned then.
It's not learned. It's tunable.
It's
I don't know if
possible
there's
to-
an algorithm to learn it.
In this paper,
Okay.
it's fixed, but I believe the author, Scott Gray, is actually working on learned sparsity using the Block-Sparse matrices.
And I think that makes a lot of sense.
Yeah.
The idea is that you really have two matrices, right? One is all the block locations, and then the
Yeah.
other one is the sets of weights within each block.
Exactly,
And sort of you can adapt both of them.
yeah,
Is the
exactly.
idea.
So the question, I mean, just to go back to this idea of this sort of a transformation here. I mean, so we have some randomly sparse connectivity here. It's not random, but it looks kind of randomish from the outside. It's not blocky. And what, can't you just take that, remap every one of those connections or bits into a block, do all your processing, and then unmap them again?
Yeah, I think that's what this basically shuffle
So-
does.
So that seems, if you could do that
If you could do that-
efficiently, then that solves everything, doesn't it?
Yeah, there's limits to doing that because there are transformations where you would have normally like small blocks in like physics problems, and you can do row and column permutations to kind of get them all clustered. But there are some sparse matrices that don't lend themselves to that. When you do the row permutation here, it upsets the order over here. So the simple example is if you have, 1001, doesn't matter which way you permute it, it's going to be the same thing.
Yeah, I think there's going to be constraints like that because if you do this and allow completely random shuffling, well, then this has the n squared property in it. You're just kind of pushing the problem here.
Yeah.
So,
Well, I guess maybe the question is how often do you doing these transformations? If the network, if the blocks and the block mappings and the block sizes don't change very rapidly, then is it possible to set this up so that the system's very efficient, once you get it going,
Yeah.
inference could be fast or something like that. Is my reading this wrong?
I think the setup that they have is pretty efficient. They were able to break some benchmarks.
Folks, if you're watching, please
So,
like the
I think
video.
with
It
just
helps out a
the
lot.
static sparsity, fixed block size and everything, you do get actually a pretty efficient system.
and the point that they're making in this figure here is that if you have block sparsity, you can now have much wider layers. Right, so it's, and with sparser connections. So you kind of increase the capacity of the network in some sense. You're not really increasing, but anyway, you can increase in that dimensionality and give it more power than a block sparse network, small block sparse network. So you lose less, and so it becomes a game of how much you can. Obviously you can't do that infinitely. You can do that to some extent and still get the benefit of the block sparsity. And giving it the
Thank you
network
for the
more
likes, I
power than
noticed.
a small block sparse network would have.
In LSTMs, there's two sort of fundamental things. One is like the number of parameters that you have, which tells you how much of the task can you remember. But then there's also the width of the network and the number of actual neurons. And as you go sparser, you can have more neurons, and that means that you can remember more from the past input history. So the parameters affect the amount that you can learn from the task itself, and then the number of neurons affects how much of the past input history can
That's
you
right,
remember.
yeah. And I was gonna get, exactly, I was gonna get
Jack
to our
Kendall
next,
from
I think that's really where the power of this is. You don't typically see too many fully connected layers in neural networks today. Instead you have, so this is the question, when is this actually helpful in real networks? So one is a fully connected feed-forward network, and that's rare nowadays. So the most common one is CNNs, and there already you have kind of block sparsity in some sense.
Yeah.
Each neuron doesn't connect to everything else, it connects to a small subset of these neurons. And then you kind of copy the weight, so this neuron will have the same weights as this. Right, so you've already kind of taken care of a lot of the problems. Now, the CNN weights themselves can be somewhat large, and so they say you can apply block sparsity to the CNN weights. But the real power, I think, is in the recurrent networks. So in that case, you have a bunch of neurons that just draw them in a rectangle.
Thanks for the sub, Moss Turner.
And because they're recurrent, all of these guys project back to themselves. So if you have n units here, you'll have n squared weights. Right, and that's, in LSTMs, it's more than that. But recurrent networks, you have that. So you're really limited in how large you can And I don't know if people have looked at convolutional structures for these recurrent waves, but it makes kind of less sense here. And so the block sparsity allows you to have much sparser connectivity here. And therefore, once you can have larger units here, you can now handle much more complex tasks and remember things further back in time.
So you can essentially sample a larger dimensional space.
Yeah. So this has been a real limiting factor for RNNs. In HTNs, we also have a recurrent structure like this, but our connections are extremely sparse. Right? So we might have, in our default NumPy thing, we have 65,000 cells here, but each active dendrite might only have 20 connections. So it's super sparse.
Talking about temporal memory.
So we can have very large. Okay. Then there's a whole connection to small world networks, which is kind of interesting. And it took me a little while I'm not sure I really understand it fully, all the implications of this, but it might be worth jumping into.
So I remember reading about small world networks in the past. I couldn't remember anything about them. So I was too lazy to look it up last night. So if there's a summary about that or a reminder that if everyone else knows what it is, like shut up. But.
Yeah, I think the simplest way to think about it is if you have n squared connections, any unit, think about this recurrent network. If you have n squared connections, any unit can talk to anyone else instantly. And you can transmit information from here to here. As it gets sparser, the number of times you have to pass information through to go from any random node to another one, so the path length will increase.
Yeah.
And so there's a trade-off between how many steps you have to go before you can communicate information versus the sparsity. And in a small world network, you can balance those two off. So I think it's like n log n is the path length.
Logarithmic, actually.
Yeah. Log n.
And it refers to small because you're not connecting very far. Is that the idea?
Yeah.
The distance is.
Yeah, the distance is small.
Yeah, so here's the definition of it, that you have small local clusters that are almost fully connected, and then you have you have for each unit, as you go further and further away in subspace, you get fewer and fewer connections.
Yeah.
So the small world comes from the 6 degrees of freedom.
Yeah.
So you have log n path length communication between them, and then there's various ways of creating these small world networks.
Okay.
And this is almost like a side discussion, but this is probably a lot we can talk about here. And people make the claim, well, the brain is small world network. I'm not sure whether I fully agree or not, because I think the issue of active dendrites makes it a little more complicated. So if you think about our recurrent networks here, you think about a layer, and if you just look at the recurrent pathways, maybe you say it's small world. But if you think about the impact of active dendrite, they're not driving connections.
Yeah.
Is it really small world anymore?
Yeah. Well, the whole thing is the brain, of course, has got this huge complex structure on top of these networks. So it's not just like a bunch of connected neurons.
If you think about region to region connectivity, there's very few hops between regions. So in that sense, it might be small world.
Yeah.
And I think they make and what they do is they deal with networks that are small world at the level of these blocks. And so they have various ways of generating these networks. So they use this as a way of figuring out how to initialize these blocks randomly. Okay. So let's see what else. We already talked about this. The other place that's helpful is you want to have really large networks and relatively large block sizes. If they're very small, then it doesn't help as much. I guess we talked about this. Is it helpful for us? It's unclear at this point whether our stuff can really fit into a block structure.
Our stuff or typical, they're making the claim it helps a lot of sparse networks, right? So.
Yeah. Right now, we kind of rely on random connectivity, and that gives us freedom to make the connections dependent on the training set and the inputs and the patterns that are there. Whereas this puts constraints on it that, I don't know whether it's constraints are too high or not. The other thing for us is we have sparse activation, which is not handled at all here.
Oh,
These are just dense to sparse. It's a dense activation against a sparse, block-sparse matrix.
how would that change things then?
Basically, here you would just treat the sparse activation as a dense vector, and you do a lot of wasted calculations.
Yeah. Lucas, do you want to say something?
Yeah, well, one point I would make is, if I understood the benchmarks correctly, they have this, both dense and sparse models have the same number of parameters. The only thing is how the connections are made. And the work we're trying to make here is to get the same level of accuracy with fewer connections, 1%, 5% connection. So what they're showing here is that you can improve accuracy with sparse models, but you still have the same amount of computation, still have the same amount of vendors. So
Yeah.
I think that's one point just to keep.
Yeah, and that's if you were just focused on accuracy. Their viewpoint is, as you make things block sparse, you're losing parameters, you're losing power, so might as well increase the size of the network.
Yeah.
So for the same amount of computation, I'm just repeating what you said, yeah, for the same amount of computation, you can get more, they show you can get more accuracy. And it doesn't have to be the case, right?
Right.
But I think the issue is the representational space is much larger, even though the connectivity is the same.
One thing that's not clear to me is these blocks, the way I'm visualizing this is that you essentially have a window over the input units and a window over the output units, and then you have sort of a dense or sparse connectivity between them. Like that's what a block is. It's some sort of like chunk of input, chunk of output, and then all those can connect to each other, which sounds like a clique in a small world network. So is that actually where small worldness is coming from? Is this block style? And do we not get that from a random sparsity?
You don't get that from random sparsity
So
unless
it's
you
coming from
construct it specifically. But yeah, here you get the small cliques are right here.
So it's a lucky maybe side effect of the way that we're getting computational benefits from block architectures, is that you get small world out of it.
I think even here you have to construct the blocks with the small word assumption in mind.
Isn't a block
You can't just do any blocks. Every block structure, every block sparse matrix is not a small world network.
But isn't a block sort of a clique?
It is a clique, yeah.
But small worldness is not just clustering, you also have to have these long range connections that follow a certain pattern.
But I don't think it's a clique, because that would assume that the input and output nodes all talk to each other in an arbitrary fashion. So it's a dense bipartite graph.
Right.
And I think in the paper, they test block sparsity with just random block sparsity, and then with small world block sparsity, and then they show the small world network outperforms the random one.
Oh, okay. I missed that.
Oh,
That's actually interesting, yeah.
Yeah,
Could you say that again?
sure. So
The
they
exact same words I just tuned out.
So they constructed the block sparsity using just random blocks, so just putting the blocks wherever, and they ran some experiments, and then they did the same thing, but instead of randomly assigning the blocks, they used the algorithms to generate a small world network of the blocks, and they showed that that one outperformed the random block
I
sparsity.
said, got it.
Yeah, and that's good, yeah. You can look at their results here, a couple of charts, looking at the speed ups you get. So here they're using a pretty large matrix, 12,000 by 12,000, and a block size of 32, which I think is their sweet spot. And they show that as you have higher and higher sparsity, you get a speed up. You know, this kind of curve is what you would expect for a perfect kind of speed up. But it's a little hard to read this. What I want to know is, so here if you look at 80% sparsity, that means 20% non-zeros. In a pure case, you'd expect a 5x speed up. And so if you go up here, it's hard to read exactly where it is. It's around 3, yeah. So I would have liked to see a version of this chart where you could really see, are you getting exactly the speed up? You know, what would be the ideal curve here? Plot the ideal curve. That would have been easier for me to understand this. But the nice thing is you do get some improvement, and I'm assuming it's going to tail off at some point. It's not actually.
Well, if you have all zeros.
Yeah. No, not just zeros, but if you go below 8 by 8 block size, which you would need to do to get really high sparsity, that's
What the overhead would be.
Yeah. And here they show the effect of, I was most interested in the effect of the block size, so 8 is much slower than 32. Not much, yeah, a factor of 2 slower. Again, here, would it be nice, they don't plot the dense version here. So it's hard for me to compare apples to apples. Yeah. What else can I do for those graphs? So basically, they get good speed ups in the Block-Sparse case. That's a good implementation. They mentioned this issue about pruning, Lucas. So that's let me go back to where it's here. Yeah. So they mentioned some of the pruning work here. That when you prune, you know you're not taking into account Block-Sparse. You're just pruning randomly. And we know that you can prune quite dramatically and still get decent performance. But they mentioned that this type of random pruning does not lead to any speed up.
Sorry, fire truck.
So is there a way, that from the way they phrase it, is there a way to prune while taking advantage of the Block-Sparse structure?
If we're running on GPUs.
If you're running on GPUs, yeah. Otherwise, today, there's no way to get speed ups from this.
Well, if you're running on any SIMD hardware, you could also take advantage of it. So the idea is, you know, how do you distill down the operations so that they are dense? And one of the things is that if you're randomly pruning, you're not going to probably get any effect. But if you, as part of your criteria, say, well, if I choose between this and this actually gets me to a slightly denser representation in some kind of space, then that could be a regularizer of sorts, you know, that tended towards something that would be more amenable to standard architectures.
Yeah, that's the way you would want to prune with that in mind.
Right.
In some sense. And again, within the block, you could still have zeros. It's that's fine too.
But it's to try to get it as.
Yeah, as compact as possible.
The other advantage is the small word networks, but that only happens in recurrent neural networks. In regular feed-forward networks, we don't get that advantage of small word.
I don't know about that. That was one of the things I was trying to understand.
Right.
I think it still has an impact in feed-forward networks. If you have a layer, multiple layers, and you want to be able to communicate information from here to any other node here, it's not one small world network, but you need multiple small world connections, I think, to increase the probability of that.
There could be a cascade effect.
Right. If it's really sparse here, there might not be any connection up to here, right? But if it's small world with where the path length is 3, let's say, then you could get it.
I think of it as like akin to distance, and there's like an expanding cone kind of as you go forward in the network.
But again, I think the more realistic issue with feed-forward networks is people just tend to use CNNs, and so you already have a lot of communication anyway. So the issue then becomes just how can you optimize the CNN kernel? Okay, and I believe this stuff, this was used in the GPT-2 or some of their latest NLPs. You know, they're really large scale.
There's sparse attention, I think.
Yeah, they use Block-Sparsity in their sparse transformer paper. I don't believe they use it in GPT-2 though.
Oh, okay. So they don't, that's interesting. GPT-2 is their largest network, but they don't use this. Why is that? You know?
Maybe different research groups.
I think it's different people working on it.
Yeah, that's my guess.
Yeah. I think they're eventually going to move towards merging the two. I guess.
I see GPT-2 as just proof that if you scale architectures without adding too many other new bells and whistles like sparsity, even that alone can get you state-of-the-art results. So I'm curious to see what will happen if they take GPT-2 and then sparsify it. And
if you sparsify, presumably you can run even larger.
Yeah,
GPT-2, they literally just scaled the model size.
Okay, but
I think that was their point, is that just by making this, on NLP in particular, there is an architecture where you just by naively scaling the model size, you can get much better.
But they're still using dense connections for that. Okay. That's good to know.
So that particular GPT-2, whatever it is that a production system, or is that more of a demonstration that, I mean, does it consume so much power that it's impractical?
It's a demo.
Okay.
I don't see, a lot of it's just transformers in general. People are starting to deploy, but I'm sure smaller than GPT-2, because GPT-2 is huge.
But
A lot of people
are using it. Like I saw a demo in Canada, and this guy was using GPT-2 just to generate sketches for like a comedy show. It was like a small thing, and he was using GPT-2. So people are using it.
I'm sure if you have a cluster of GPUs, you can run inference on it.
Yeah, but at a high level, I think, generally, machine learning world is very constrained by what you can do with GPUs today. And so the only way you could even really consider sparsity is using these block structure. And you can't really even think about random sparsity and still hope to get speed ups, which is a problem.
I mean, Sparse is decent, but that's for arbitrary sparsity. But this is really just like a more fine-tuned, more highly optimized.
Yeah, they mentioned that cuBLAS was faster than Sparse.
So Sparse, I think 8.0 for whatever reason showed almost no speedups over normal cuBLAS operations, but I think now they're at like 9.2. And I don't know what they did, but it's like 20 to 30x faster than what it was.
So this is since this paper was released.
Yeah.
Okay, so you would expect their conclusion here to be different now. That Sparse with Block-Sparse matrices would be.
This would certainly be better, but Sparse now is better than it used to be.
Okay. Or arbitrary sparsity.
Yeah, for arbitrary sparsity.
But for block sparsity, I think they say, at least in this paper, cuBLAS is still quite good. It's just a bunch of dense matrices.
I don't know for Sparse, but I know for the MK library, they added a construct that tried to have a gather operation to try to consolidate stuff and throw it out. I'm just learning it, so I don't have, the 7-letter acronyms memorized here. But I think a lot of this stuff devolves down to like hardware to have scatter gather of the things to say, okay, these things are out here in memory. How do we distill it down, run it through our type functional unit, then blast out? If we really need to blast out again, or do you go into some representation that goes through all of that? So you see that on DSPs, you see that on a number of other architectures, and that's really what it comes down to, is how can you rendezvous the data elements together into a type functional unit.
Do you have a sense for how good Sparse is, and what would it?
From what we've seen, it's decent. It's certainly a speed up over the naive implementation.
Yeah. So if in the naive, if we have, let's say, 5% non-zeros randomly, in the naive implementation, you get 0 speed up. In the perfect implementation, you might get a 20x speed up. Where would Sparse stand?
What have we seen?
I don't have an exact number for that, but for us, Sparse has been valuable because we're using matrices that are just larger than what can fit on GPU memory. So maybe 50,000 by 50,000, and that's with like 98% sparsity, and that just can't be done with standard methods.
Okay, so it's just a memory, just even from a memory.
I think there was. Richard said that there was like a 20x speed up.
Yes.
Right. Just in general.
Right around
Okay.
20x, 25.
So if you have 1% non-zeros, 99% sparsity, you get 20x speed up.
Maybe 20x. I'm gonna double check that then.
Okay. That's good to know. I don't think those are integrated into PyTorch or anything yet.
No, they're
That
not.
should be really nice.
PyTorch is painfully slow
Yeah.
Yeah,
with sparsity.
even TensorFlow, I think it's pretty.
I don't know about TensorFlow actually.
TensorFlow is better, but still not as good as just Sparse or block sparsity.
Yeah.
I think they're working on it though at PyTorch, so
There was
Yeah.
one guy yesterday who was pretty interested in building that, like
Yeah.
sparse to model for PyTorch. I think he's doing research on that.
Oh, okay, cool. Oh, that'd be really nice.
Yeah, we met in a PyTorch hackathon.
Yeah, I think when Lewis looked at it, they were just converting things to decimals.
yeah.
They convert to decimal.
What does that help?
It's slower.
Yeah.
It's a quick hack, right?
Yeah. Yeah. Okay, anything else? Matt, do you want to stop the live stream? Yeah.
Yeah.
just gonna say bye. Thank you guys for watching.